today we're going to be discussing the divergence theorem. The divergence theorem is very closely related to Green's theorem, and that Green's theorem took a path around and was a line integral that took a path around a closed space, and Green's theorem then considered the area inside of that path. The divergence theorem takes a surface integral, and we do the surface integral, and instead of considering the surface, it considers the volume that is enclosed by that surface, and it takes the triple integral over that volume. So it's very much the Green's theorem of surface integrals. And the only requirement that you have, there's actually two of them that you have to keep in mind. One is it has to be the surface integral over a vector field. So it's over a vector field, not just the surface integral over any random function. And also, it has to be a simple solid region that is created by these surfaces. And by simple solid region, this is really any region that can be integrated with a triple integral. So with a single triple integral. So when we learned how to do triple integrals in chapter 12, if you can integrate with a single triple integral, that's a simple solid region. So this is an example of one on the slide where you have some planar surfaces, some non-planar surfaces enclosing a region. And so the divergence theorem uses the divergence, which we learned about in 13.5. And so you take the divergence of the vector field, and it's the triple integral of the volume over the volume of the surface, the volume that is created by encapsulating with the surface. So that's what we're going to do today. And that's the divergence theorem. And it's generally a ton easier than doing the surface integral. Because remember, to do a surface integral, we had to parameterize the surface in terms of two different parameters. We had to find the partials. We had to do the cross product and then the dot product with the vector field. In this particular, if we were looking at this solid that was on the screen, there's 1, 2, 3 surfaces that make up this solid. So we have to do the surface integral 3 times and then add those up. Whereas here, we can take the surface integral in one triple integral. So if you're able to do the divergence theorem, generally it's going to be easier. I've been doing some experimentation with problems in 13.6 to see if it's easier, and mostly it has been. So yeah, just keep that in mind moving forward when you see problems that allow you to use it. But again, it has to be over a vector field, and it has to be in an enclosed space by that surface. So let's try this one. It says find the flux of the vector field over the unit sphere. Remember that to calculate flux is the surface integral over the surface f of the vector field dot ds. And since we're going to use the divergence theorem, it's the triple integral over the enclosed space by our surface of the divergence of the vector field with respect to volume. It'll probably be good to start with the easy part, which is just finding the divergence of the vector field. So just a reminder to calculate divergence, it's going to be the partial of the vector field, vector value function p with respect to x, plus the partial of q with respect to y, plus the partial of r with respect to z, That is the divergence formula. So essentially you're taking the partial of each of those vector value functions of your vector field and summing them. So that's the divergence formula. So in this case, the divergence of F is going to be the partial of Z with respect to X, which is 0, the partial of Y with respect to Y, which is 1, and the partial of X with respect to Z, which is 0. So the divergence of our vector field here is 1. Any questions on that? So now we have to consider that our surface, and again, it has to be a closed solid region. So a sphere is definitely closed, and it's simple. It doesn't like cross over on itself at all. So that would indicate we probably want to go to spherical coordinates. However, let's just set up our little triple integral. So it's our triple integral over the sphere, x squared plus y squared plus z squared is less than or equal to 1 of 1 dv. What does this mean? Yep.
That just is the height of the sphere.
Yes. So if you take the triple integral with respect to volume, and the integrand is just 1, it's just the volume of a sphere. Well, what's the volume of a sphere of radius 1?
4/3 pi.
4/3 pi r cubed. So because our integrand is 1, it won't always be 1. But in this case, because it's 1, we can avoid doing the actual triple integral because the triple integral with respect to volume of volume is just volume. Yep.
Is there any trick if it was like 2 on how to do it?
If the integrand was 2,
Yeah.
you could pull the 2 to the outside,
Okay.
and then it would just double it.
So if it's a solid, if it's a whole number with no variable.
Right. Yeah. Other questions? Let's actually do one where we have to take the triple integral. So for this one, we're going to use the divergence theorem to evaluate the surface integral f dot ds, where our vector field is x, y, I. So that's our x component. Negative 1/2 y squared j plus zk. And the surface consists of 3 surfaces. So we get z equals 4 minus 3x squared minus 3y squared on the top. X squared plus y squared equals 1. Oh, I think I'm cutting some stuff off. Let's make it. Consists of 3 surfaces. Z equals 4 minus 3x squared minus 3y squared for z 1 to 4 on the top. X squared plus y squared equals 1 for z between 0 and 1 on the sides, and z equals 0 on the bottom. So the surface consists of 3 surfaces. So you can imagine without the divergence theorem, we would need to do 3 surface integrals, which would be quite laborious. So using the divergence theorem, we can replace 3 surface integrals with 1 triple integral. And I'm going to begin with a picture. Do we know what z equals 4 minus 3x squared minus 3y squared is? Anyone know what that is? Yeah, it's a paraboloid flipped upside down. The x squared minus y squared bit is negative, so that flips it upside down, and then it's moved 4 units up. And that's going to be valid for z between 1 and 4. So let me begin to draw that. And then I have a cylinder that x squared plus y squared equals 1 from 0 to 1. So that means it essentially just goes straight down to the xy plane. So I have curvy paraboloid from 4 to 1 on the z, and then from 1 to 0, it's just a cylinder. So straight, and then it's more curvy from 1 to 4. Questions on the picture? All right, what coordinate system do you think we should use for our triple integral? Yeah, in 3D, we're gonna just call that cylindrical, which is just polar with a z. So z on the bottom is bounded by the xy plane. So we're going to do 0 to z to 4 minus 3r squared. Because when we look on the bottom bound, the z is the xy plane. The top bound of the z is this dome, which is our 4 minus 3r squared, which I just put the x squared minus y squared as the r squared. Any questions on converting that to the polar? Okay. And then what are the bounds of our r? We have to fill in the volume. Go ahead.
0 to 1.
Yeah. So the fattest the circle gets, the widest it gets, it goes from 0 to 1, doesn't go beyond 1. When you look at the intersection of these two, the paraboloid and the cylinder, it intersects at 1, okay, at an R value of 1. So if you want to write, you intersect this and this, they intersect right there at z equals 1. And at z equals 1, the radius of the circle is going to be 1. And then it has to go into 0 to fill in that volume. Any questions on that? All right. And then our theta goes from 0 to 2 pi because we're doing the full part of the circle. Questions moving forward? Okay, so we have our bounds. I think that's the hardest part. We do need to find the divergence. It's called the divergence theorem. So we do need to know the divergence of our function. So we're going to have to take the partial with respect to x of our x component. So that's going to be y. Partial with respect to y of our y component. That's going to be negative y. Partial with respect to z of our z component. That's going to be 1. So the divergence is going to be 1. That is just a coincidence. Don't count on that moving forward. All right, so we're going to do the triple integral of the divergence with respect to volume. So remember the conversion between Cartesian and cylindrical is r dz dr d theta. And we have our z bounds from 0 to 4 minus 3r squared. And then 0 to 1 and 0 to 2 pi. So the inner integral is just going to be ZR, and filling in the bounds, it's just going to be 4R minus 3R cubed. And then I'm just going to take out the 2 pi. Oh, those must be wrong. 0 to 2 pi. Let me fix that. 0 to 2 pi. So I did the d theta already. There's no thetas, so that integral I just pulled out. I did the inner integral. That's just RZ. Evaluated that at 4 minus 3R squared and got 4R minus 3R cubed. And then I'll do the R integral. That's going to be 2 minus 3/4. That's 5/4. So 2 pi times 5/4 will give us a final answer of 5/2 pi. Any questions on that?